Class, I had a really interesting question come in today, and it made me think about just how useful the answer would be to you guys, partly to do right now's homework on planes, but especially for some of the stuff that's coming up later. So I just wanted to take a minute to share some information with you so you can kind of connect prior knowledge with current knowledge about planes and have some tools to kind of play around a little bit with understanding this stuff a little bit better. So I'm going to try to activate some prior knowledge here. If you can think about lines in 2 dimensions, right? We're back to like just the X, Y, there's no Z. A couple of things to remember are if a 2D line is a vertical line, then you get an equation where there's like just the one variable, like X equals 2. So obviously, if we go to Desmos and we don't do like a 3D graph, suppose we do like a Desmos graphing calculator that's just a normal calculator, then if I have something like this, then what that means is X has to be 2, but Y can be anything. So we can have a line on the XY plane where there's only one variable. Or we can have a slanty line where there's changes in the X and the Y if we have something where we, have both an X and a Y. So if you get down to a single variable, then you end up with that variable where, by the way, it's like parallel to the axis, right? And in other words, Y is 5 on this horizontal line, but X can be any value at all. That's why we don't bother mentioning the X. Whereas for something like 2X plus 3Y equals 6, then we end up with something where we have more of a slanty line, and there's this relationship between the X and the Y where they have to satisfy this relationship. So you can actually extend this information up to the 3D model, and you can actually even extend these exact equations up to 3D. A tool that I like is this desmos.com/3D. And so let's talk a little bit about how that compares. So couple things to remember with this is that you can play around with it. You can zoom out, you can rotate. So I'll show you some of that stuff. So we can actually have an equation of a plane where there's only one variable. So an example I have here is Z equals 0, Z equals 2. Let's look at what those look like. So if I do Z equals 0, notice that that actually just highlights the XY plane. But if I do Z equals 2, and I can kind of drag this here to kind of show what it looks like, this is parallel to the XY plane, but it is height is Z. In other words, I can think of this like Z has to stay 2, right? But X and Y can be anything, which is a little bit like what we were seeing before with those horizontal and vertical lines in 2D. We can do the same thing for something like X equals 3, but that one's now going to be parallel to the YZ plane because Y can be anything, Z can be anything, but X has to be 3. So as an example of that, I just made something kind of fun. Do you see how now it's kind of back to a 2D graph? So with this, sometimes you want to re-click extend to 3D. So now if I turn this, I can see how this is parallel to my XY coordinate plane, but it cuts through at the X value of 3. So I can have equations of planes with just one variable. However, that means that it's going to be a plane that's completely parallel to one of my nice coordinate planes. Now, I can also have planes with 2 variables in the equation. So something like an example I have here is X plus 2Y equals 4. So what I like to think of if I want to envision that is basically taking that line sitting in the XY plane of X plus 2Y equals 4, which let's go ahead and graph that without it being extended to 3D. See how that's just that line in the XY plane? And when I am saying, no, I'm not talking about a 2-dimensional line, I'm talking about the plane X plus 2Y equals 4, which is basically saying it has to follow along that line, but Z can be anything. So we can extend that line up and down infinitely to make a plane. So that would look like this. And you can kind of see, if you go like top view down on the XY plane, you can see you get that equation, x plus 2y equals 4. But if you kind of turn it, you can see how it's created a plane. And so that's a nice way to be able to envision what a 2-variable plane would be represented by. And you can do the same kind of thing with this one right here. Y plus z equals 6. If I take off extended 3D, it is going to graph, well, apparently it extended to 3D anyway. It's going to graph the line, and see how I couldn't really see it well. It was kind of chopped off. I'm going to zoom out just using my mouse. I can see how that looks like the line. Y plus z equals 6, kind of like x plus y equals 6, except that with the y and the z, right? And it extends it along so that it includes all values of x. So x can be whatever, but y and z have to satisfy this relationship that they add up to 6. And these, by the way, are always going to be perpendicular to the plane where the corresponding line is. So if you look at this right here, this plane is perpendicular to the YZ plane. And similarly, the last one, let's see if it saved it. No, what was it? Let's see. X plus 2y equals 4. If I extend that to 3D, you can see that that is going to be a line that is perpendicular to the XY plane, just like this. And so that's kind of a general way that you can envision and create these. So the slantiest planes of all are the ones with 3 variables in the equation. So a nice example of that would be something like this: x plus 2y plus 3z equals 6. And with that, when we have the graph, sometimes it helps to drag and turn it a little bit. You can kind of see where things are. But sometimes people get a little overly reliant on these 3D graphs. So I also like to kind of talk to you guys about how I get a quick sort of snapshot of what this looks like more algebraically. And this, by the way, strategy will end up being needed later in the class. You have to be able to do this when you're doing some of the future work in the class. You'll have to be able to identify the parts that I'm doing here. So I usually like to graph something like this using intercepts. So if I'm going to sketch something like x plus 2y plus 3z equals 6, then I'll do things like say, okay, well, what if x and y are 0? Then z is going to have to be 2 in this case. So 0, 0, 2 is one of the points. And you can kind of see, I think I've gone like upside down at this point. Here we go. Now we're right side up. You can see 0, 0, 2. I think you can see my cursor. So x is 0, y is 0, z is 2 would be that point kind of up here on the z-axis. And you can do the same thing when you set the other variables equal to 0. So like x is 0, z is 0 means y is 3. So 0, 3, 0 is also a point on the plane. So that would mean x is 0, z is 0, y is 3 would be this point right here. And last but not least, if I set y and z equal to 0, x has to be 6. So that means this point out here is at 6, 0, 0. So plotting those 3 points and then saying now the plane extends kind of through those points is a nice way to do it. But also it makes it easier to draw your own little sketch. And many, many, many times what you're going to be looking for in the future is going to be kind of more of a snapshot of how do planes cross, particularly most commonly the XY coordinate plane, and maybe what region is trapped within, for example, the first octant. So being able to picture those 3 little intersection points with the axes is really a handy skill for you to have for your future self later on in the class. Okay, so hopefully this video helps you envision some of this. Again, remember that the website, there are a few different websites that are nice to use. The particular one that I'm using here is desmos.com/3D. You can also use CalcPlot 3D, which is a nice tool. You just have to kind of get used to the settings a little bit. But thank you for taking the time to watch this. I think you'll find it really useful as we continue on in the course.